Well, hello everyone. We are going to talk about resonance structures today and how to do resonance. So, let's start by explaining what resonance is. Resonance is fake. It's fake news. Let me give you an example. Like your dating pictures, right? If you're on a dating profile, you might have one picture of you that looks amazing and another picture of you on the other side that looks amazing, and all sorts of these pictures that might look amazing. And those are all real sides of you, right? But it takes a whole bunch of those pictures all together to give you an overall representation of what you actually look like. So one might be, showing you smiling, and one might be showing you angry or whatever. But overall, you have to overlay all of those pictures to get you to get an actual representation of what you look like. Okay, and that's the same thing with resonance. So for example, nitrate, and we'll do an example of nitrate here in a little bit. This is nitrate. It's a polyatomic ion, in case you forgot. And this is one structure of nitrate, okay? Now this whole thing kind of moves around, where we'll eventually find out that those bonds go down there and that comes up there, and then we get another structure of nitrate. So we get this. And then now this has become a double bond here. And now this one has become a single bond. And the negative charge is now over here. And then another structure of nitrate might be where we're now taking these bonds and moving them down here, and these and moving them up here, or these and moving them down there, and those and moving them up there. So we're always just kind of moving things around. So now we have an N, and over here this one was the double bonded one. Now let's make this one the double bonded one. So none of these are a lie. They all represent nitrate, right? And all together we do something like this. We put brackets around them to indicate that they're resonance structures. So all of them works, but you need all of them together to give you a full picture of what nitrate is actually doing. Nitrate isn't at any one point just this, or at any one point just that. It's actually a culmination of all of these. And I forgot the positive charge on this nitrogen over here. All right, but it's a culmination of all of them. So the actual nitrate looks something more like this, where it doesn't have a double bond here, it doesn't have a double bond here, it doesn't have a double bond here. It's kind of splitting that double bond between all of them, and this is the actual structure of what nitrate looks like. So even though we draw arrows going back and forth, it can be confused with equilibrium. This isn't a reaction that's occurring, so these electrons aren't actually moving from here to here. We're just trying to find a way to represent what nitrate overall looks like. These electrons are actually delocalized, meaning they're not just here. They're kind of hanging out in all three of these locations, and being shared equally among the oxygens. And the only way that we can really show this is through resonance structures, and that's why we use them. Okay? So we're thinking of it as rearranging bonds, not rearranging atoms. You're not drawing, these are not isomers. Okay, these are exactly the same molecule. So an isomer might look totally different. Trying to think of a good isomer I could draw off the top of my head, but an isomer, this might be an isomer of butane, but so might that. So each of these things have 4 carbons, right? Each of these things are C4H10, but their structures are very wildly different, right? So these are not the same. These are called isomers. Whereas resonance structures are not isomers. All right, let's get into some rules. So when you're drawing resonance structures, you can only move electrons. Right? You can only move electrons. You can't move atoms around. Like over here, this was different with atoms, so that is not a resonance structure. Let's talk about a few different examples. So you can move lone pairs, and turn them into bonds. So let's say you have something like this molecule. So here you have lone pairs, and here you have an electron deficient, a positive carbon down here, right? Don't forget that in order for it to be a carbon, this thing has just one hydrogen on it right now. Okay, so what you can do is you can take these electrons right here and move them down here. So now this negative, these electrons can go toward the positive thing. Remember, we're always moving electrons generally from the negative to the positive thing. Okay, so now this gives us something like this. And that would be a strong resonance structure, okay? We took lone pairs and we made them into a bond. Now this carbon no longer has a positive charge because, again, just to remind you, I won't do this a lot because this is, at this point, you guys should be getting this pretty well. We had a carbon with one hydrogen on it. That's the only way we could get a positive charge. Now you still have a carbon with one hydrogen on it, but now carbon has four things around it, which is why it's neutral. All right, the other way you can do it is you can move bonds and turn them into lone pairs. So one fun example, it's kind of hard to start without already having some kind of lone pair on this thing. So let's say you have something like this. That would be a negative charge. And this usually happens, especially if you have a lone pair and then it's like a single bond here and then a double bond here. And anytime you have a little kind of thing right there, we're going to be moving electrons around. So I said the bonds would turn into lone pair. And what I mean by that is if these electrons hopped down here, meaning lone pair turned into a bond, like we did up here, then this bond would have to move. Because again, there's a carbon right here, it's got one hydrogen on it, and you know carbon can't have 5 bonds, it has to stick with 4. So if these electrons move down here and become a double bond here, then this bond has to move, and this bond will move to this carbon right there. So you can always move things to adjacent stuff. So you can move a bond to a lone pair, you can move a lone pair to a bond. And what we end up getting on this situation is now this lone pair right here is now formed a double bond. And don't forget that this bond right here these electrons went onto this carbon. So now the negative charge is over here. All right, the other way we can move electrons around is bond to bonds. So we can shift around in what's called a pi system. So there's a few different ways I could go about this, but I had a different example, which maybe I'll do in a second. But one of the most common examples is simply benzene. Especially if you have what's called a conjugated system, and you'll get into conjugated systems a lot more in organic too. There are some very specific things, but for right now, we'll just think of a conjugated system as kind of something that has every other bond is a double bond. And what can happen is this bond can move there, that bond can move there, and that bond can move there. And this thing can resonate. Whoops. No, I screwed up. This thing can resonate, need to look at the paper, not the camera, to that. Okay, so now all the bonds have moved. Oftentimes you'll see benzene in some old school stuff as drawn this way, where there's like a circle around it going through it. That's just to indicate that it's resonance, and this is its overall structure, right, that we're drawing, the average structure, or hybrid structure as it might be called. The other example I was going to give you, just so you can see it, would be if you have, let's say, something with a positive charge, and this is kind of really common, where you'll have a cation, or a carbanion as we're going to call them. I don't know why I said carbanion, it's a cation. And we're going to move this double bond. Again, always moving from electrons to the positive thing, so we can move this electrons over here to satisfy the fact that this carbon was positive right here. But then when we do it, you can kind of picture, we took this double bond and we flipped it over here. So this carbon still will have a double bond. So let's draw it real quick and see if this makes sense. Okay, so this carbon still has a double bond. It had one here, it still has one here. Now this positive charge is happy because it's got this new electron, this new bond right here, so it's totally cool. But think about this poor one right here. It no longer has that double bond. So you took that double bond and you moved it over here, but in doing so, this one became deficient. It lost its bond, and that's why that will be the thing with the positive charge now. So when I think about double bonds and stuff moving, I always kind of just picture moving it this way, and then whatever thing lost that double bond will now have a positive charge on it. Okay, you're never going to move a single electron. Okay, so you can't just take a bond and move. We know that bonds represent 2 electrons. You can't just move 1 electron someplace and 1 electron another place. So for example, let's say you had something like this, and you got this. You can't just be like, actually, let me give you a better example. That was the next example. You can't just be like, hey, I think I want this double bond to break into 2 parts. I think I want 1 electron up here and 1 electron down there, and then this would resonate and you'd get something like this with 1 electron there and 1 electron there. You can't do that, okay? You can't break apart a bond into 2 different electrons. Those are called radicals, and they're aptly named. That would be a very radical thing to do. The next one I don't have a lot of examples for. We'll kind of talk about them as we go, but you can't break the octet rule. You can have less than 8 electrons. So an example being something we just did. This carbon right here with a positive charge only had 2, 4, 6 electrons around it. You can have less, but you cannot have more than 8 electrons. You cannot have more than 8 electrons around it at any given time. If one atom gains electrons, then the other one must lose. So kind of like we took that double bond and we shifted, that carbon had electrons, and when we moved it, it lost. And then the exception would be third row elements. S and P can expand their octet, but only specific cases. So for example, sulfate might be a common ion you've drawn in your life. So sulfate is SO4, 2 negative. And it looks something like this. I'll draw all the dots for you. Where this is negative charge, this is a negative charge. Both of these oxygens are neutral. And that's how you get the 2 negative overall. Now notice sulfur has 2, 4, 6, 8, 10, 12 things. Okay, so anything in the 3rd row or below in the periodic table, so if this is the 3rd row, anything here or below, we can expand the octet. But you won't run into it too often in organic chemistry, but it is good to know. All right, conserve charge. So the charges must stay the same across all resonance structures. Whether you realize it or not, we've already been adhering to this rule. So for example, if we have something like this, I could technically, if I felt like it, take those electrons and put them there. Okay. It's not the most stable thing in the world, as we'll come to learn with the stability rules, because you're putting a negative charge on a less electronegative atom. So we're purposely putting a negative charge on a carbon here, meaning it's not stable, but it can be done. So we move from a double bond onto an adjacent atom. But in doing so, it might be really easy to forget that we did something. So if I look at this overall charge, this is -1, right? But if I looked over here, this is -2, and that can't happen. They have to be the same charge overall. So -1 and -1 would be a -2. Means I'm missing something. Don't forget that when you took that double bond and you moved it, you deprived that carbon of the electrons that it once had, and this now has a positive charge. And that's why this structure right here would also be -1. You could even go crazier if you wanted to. Actually, that's already pretty crazy, I'd say. This is pretty unstable. So I think my point was proved. But I could have taken, for example, these and popped them down and then put those there. And then that would have been another situation I could have done. All right. So stability rules. All right, so this thing is not stable. And I know it's not stable for a variety of reasons. One, it has almost full octets, except for this one, right, is now a deficient octet. The charge, the negative charge needs to go in the more electronegative atom. So here, this is okay. This is good. We've got a negative charge on a more electronegative atom, which would be oxygen. To remind you, electronegativity goes up and to the right like that on the periodic table. But over here, we have it on a carbon. And so whenever you have this, and this is a carbanion, anytime you have a negative charge on a less electronegative atom, when you don't need it, it's going to be less stable. Okay. You want to put the positive charges on the less electronegative atom. So here we have a positive charge on this. So this was decent. Okay, that's doable. But you also want to avoid placing charges close together. So here I have a negative, and on the very next carbon I have a positive, and on the very next oxygen I have a negative. Okay, so in this thing right here, we did not have a full octet. We did not put the negative charges on the more electronegative atom. So like if we had left this alone, that would have been better. We did not put the positive charge on the, well, actually, I guess we did put the positive charge on the less electronegative atom. Okay. And we did not avoid putting charges close together. So this structure would not be stable. Okay. Connect structures with double-headed arrows and use these, and then again, resonance is a blending of structures. It's not going back and forth. It's not an equilibrium. Okay, let's look for some common patterns that you're going to see so you can kind of get used to knowing what's going to happen where. Okay, so if you look for an allylic system where you got a pi bond next to a lone pair, like this, anytime you see something like this, you're going to know that things can move, because you have electrons here and electrons here that can all move toward each other, away from each other. And what's going to happen is these electrons, they can pop down here. But now we have a carbon right here, and it can't have that many bonds. Don't forget there's a hydrogen on there that we don't see. So it can't have that many bonds, so then these have to pop up and go onto that carbon. And so you'd get something like this. And then that double bond would now be there. So this is something you'll see kind of quite frequently, in fact. Again, all the charges on each side add up, you're good. But there's no avoiding having a negative charge on a carbon, no matter which one you do. So resonating, you're not going to have a more stable structure here. They're both relatively equivalent. In fact, they are the same structure if you flip it around. Okay, the other thing, pi bonding next to a positive charge. So if you have a pi bond, again, which is like we said pi bonds are like double bonds or a triple bond. So if you have a double bond next to a positively charged thing. So let's say I have and I've got some kind of double bond to an N here. And anytime N has 4 bonds, it's positively charged. Okay, so we have a pi bond here, and it's next to this positive charge thing. I'm going to show you a different setup too. In this situation, here we have a negative right here, and we have a positive here. Don't forget, electrons are always moving from the negative to get to the positive. So these electrons can move down here. But if it does that, carbon then has 5 bonds, it can't. So these electrons can then move up on top of that nitrogen and be like, I'm coming for you, positive, don't worry. And then what you're going to get is something like this. Okay, so those oxygen became double bond, and that goes on there, and now you have fewer charges overall. Over here the total was 0, over here the total is 0. This one's actually going to be more stable. Okay, then the other one I want to show you is if you have a positive charged carbon, like that. And I hope you're getting these enough that you kind of have an idea now. Remember, the electrons move toward the positive thing. They're not going to hop up here on this carbon. They could, kind of. No, they actually couldn't. They'd break the octet rule. But they can move this way. So you can take these double bond and move them over here. So we're going to take that double bond and move it over here to satisfy that positive charge right there. Let me clean this up a little bit. And if you do that, though, hopefully you remember you're going to deprive that carbon of its electrons. We draw the same exact skeleton every single time, but now the double bond's moved there. And now the positive charge, which was on this carbon, is now got to move to this carbon. Okay. This next one, if we have something like this, so we have pi bonds next to other pi bonds, then if this one moves, right, which we could do, we could break this down and move it one at a time. So you're taking this pi bond and moving it over here. Now you've created a positive charge right here. So then hopefully you agree the next thing that would happen would be that double bond goes over there. So now we got one there and one there, and now we have a positive charge at the end there. And we'll come to know this is a secondary cation. This one is the carbocation, and this one is a primary carbocation. You'll learn about stability in a little bit, but this is actually a totally normal thing that could occur prior to a reaction. So this is when double pi bonds move. The other option that I showed you, or other example that I showed you, was just benzene. Don't forget, in something like benzene, all of these could move, and you would get boop, 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 something like that. And then last but not least, if we have atoms with incomplete octets, the most common of that would be a carbocation, which is a positively charged carbon. So let's see. Let's see if we have something like this. And it's totally happy. But then you move the electrons up here for the oxygen. You're like, oxygen could move that way. It likes electrons. Electrons would move toward that. But what you've done is you've created this carbocation down there. This is now a negative charge up here. And we know that carbocations have an incomplete octet. So if you have an incomplete octet, some kind of electron is looking to bond with it, or some kind of electron is looking to move toward it. So you could take these electrons and move them right back to where they were, or you can move those electrons right there and move them to this location. Don't forget, you can't ever just take electrons and move them onto the carbon atom because they're too far away. You can only move to the adjacent thing. So because this double bond is touching this carbon, you can move the double bond to the other side of that carbon. And then we'd have that. Don't forget, you now have a positive charge down there because you deprived that carbon. So an incomplete octet, what I mean by that is that this carbon only had 2, 4, 6 things around it. There were no hydrogens on it, and that's where you've completed, or that's where you've gotten an incomplete octet from. All right, I think that's about it. That gives you a lot of situations where you'll encounter resonance, and I hope it made some sense. I would go do some practice problems in your book and make sure you really got them down, and just note that they can get a little more complicated, but this is the basics for now to help you get through. So, all right, hope this helps. Bye.